Welcome. Today we'll be looking at acceleration of a particle along a circular path. Now, a textbook I recommend for further study is Theory of Machines by R.S. Kumi. Now, in this video, we'll only be looking at a subsection, which is the topic here. Now, in this circle portion, this we're going to assume is a circular motion. Now imagine you have a string, you're holding out a string and you're holding it at this point, and this is the length of the string right here, and you're winding, swirling maybe a stone which is attached to the string, and it's going in this part. Now at this point E, we have a velocity. Now, one keynote is the difference between speed and velocity. Speed is magnitude of velocity. It's a scalar quantity, while velocity is a vector quantity, which means velocity deals with direction. Now, the velocity is acting tangential. Think of it this way. Let's get practical. Stand up, stretch forth one of your hands. Now stand on a spot and move in a circle. Turn yourself in a circle maybe 1 or 2 times while your hands are stretched out. Now you notice that your hand is not moving away from you, else your hand will be detached. Your hand is still attached to you. Now look at the tip of your hand, the tip of your finger. As you're swirling and moving around, you're practically making a circle. But let's say at a point which we'll call A, as you keep on moving, swirling, your velocity at point A is tangent to the circular path you're making. So also your velocity at point B is tangential to the path you've created at point B, to the circular path. Now we can resolve this into a vector diagram, which we have here. Now simply putting, this vector diagram is just showing pictorially, clearly, directions. So this is how it's resolved. Now this velocity here is what we have here. Now if you agree with me that as you keep on spinning, let's say you start at point E, the velocity at which you started at point E, as you swing, your velocity increases. It's just like how in linear motion, when your body starts at rest and it accelerates, the velocity v2 will be greater than v1. So at point B, the velocity here is greater than that at point E. Now, another thing to take note of here is the angle. The angle is showing us how much the radius has rotated as a particle moves from A to B. Now, at point A, moving on to point B, the velocity changes from A to B. Now the angle from A to B will be the same angle traveled by the velocity change from A to B. This is what we have here, changing theta. Now coming over here, this point O is our reference. Now this is vector V from here previously, and over here this is vector V plus change in V, which we agreed is the increase in velocity, because the string is happening this way, so velocity increased from A to B. Now completing the vector triangle, you'll notice broken lines here and here. Now those broken lines, as noted here, they do not represent the velocity or acceleration vector, that is A to C. What then does it represent? It's just a construction line that is used to resolve change in V into the tangential and normal components. As I said, AC is just a construction line, it's just an extension of the vector V. Now, revision of the topic vector in mathematics will help a lot in understanding this. Now, from vector, we know that if you have a vector triangle, let's see, ABC, represented by vectors A, vectors B, and vector C, and the direction of C is this way. C is going to be equal to A plus B. Now taking this concept and coming here, now this is the main focus. Okay, all this is just an extension to make everything easier. We'll come to that in just a sec. Now, OB is equal to vector V plus, there's supposed to be a vector here. Now, this is the sum of this here and this here, so we know AB is going to be change in V. Now Now from that theorem, we know this is supposed to be changing VEB. Now remember, anytime we mention acceleration, we are considering change in velocity by change in time. Yeah. So remember, now we are building upon previous premise. Back here, we know this to be our tangential velocity. Now we're trying to sorry about that. Now we're trying to get our tangential component of acceleration. So we need to incorporate that here. Now AC is an extension of this vector V, the tangential velocity. Yeah. Now CB from here to here, it is an extension to help us with the normal velocity. That is the normal component of the velocity. Now let's move on. Right here is the tangential component of the acceleration, ET. We also come to tangential component of the velocity. Now, tangential component of the acceleration, remember, it is contained in, we need it along here. Now remember again, acceleration, we're dealing with change in velocity, but our change in velocity is way over here, but we need it to be part of this velocity vector here. That's the use of the extension EC. Now let's come to that. EC is same as OC subtracted by OE. This will give us remaining portion of EC. Now we represented it here. Now what is OC? Now just take a deep breath. Just like in maths, when we have a triangle and an angle, let's see, theta, call here B, call here A, call here C. B is same as C cos theta. So also A is same as C sine theta. Now keep this in notes, we'll be using it here. Now from the explanation, OC will be, now in this case, this is what we're dealing with, V plus delta V. So it will be V plus delta V cos the angle, which is theta here, which is what we have here, subtracted by OE. And what's OE? OE is simply V. That's what we have here, divided by change in t, because acceleration is change in velocity divided by change in time. So this is how we have this here. From here we simplify forward. Now at point A, right here, we're dealing with an instant, so delta t is approaching 0. let's put it as that delta t approaches 0. Now taking that limit, again here pre-calc will be very essential. Taking the limit, now let's do a little observation. We have this angle delta theta over a certain change in time, which we represent as delta t, which means if delta theta is 0, there won't be an angle change, which also means delta theta will approach 0, right? Because think about it. Let's look at it straight line motion to make it simpler. If I start at point A and move to point B within a time interval, let's say t. Now, if there's no time interval at all, it just means I'm still at the same point. Yeah. Now, this delta theta helps in calculating angular distance, which is used in circular motion here. So we can kind of use that analogy here. So I'll just put it as a note. You can just jot this down as a note. Now coming back here, for the benefit of those who aren't so strong in pre-calc, let me simplify this a bit further. Now, as delta t approaches 0, down here in the denominator, we're going to have 0, and we know anything divided by 0 leads to it being undefined. Now, to avoid that, we apply L'Hopital's rule, which simply means or tells us to take derivative of the numerator so take the derivative of the numerator and take the derivative also of the denominator. Now doing that, it will give us dv divided by dt. Now we know that v is equals to omega r, so this is simply d into brackets omega r divided by dt. And this is equals to r d omega over dt. Now we know d omega over dt is equals to angular acceleration. Hence, we have this multiplied by r. Again, please also go over your calculus. Now let's go over this quickly. So basically, simplifying this limit here, it will be limit of change in t approaching 0 of change in v over change in t on simplifying the numerator. Now from L'Hopital's rule, we know we take the derivative of the top numerator and denominator, which will give this. Then simplifying based on this formula, which is v equals omega r, and omega equals the omega over dt. When we substitute this into v here, all that will simplify and give us this. So feel free to rewind the video and go over it again. Now this is the derivation for our tangential acceleration. Now our normal component of the acceleration we'll be deriving now. Again, we go and reference the vector diagram. This is our vector diagram right here. Our normal acceleration is represented by CB. Now again, from our knowledge on angles of a triangle, we know that CB will be represented by OB sine theta, and our OP is given as V plus delta V. Now that's what we have here. Again, acceleration is change in velocity divided by change in time. So this is what we simplified out right here. Again, limits, taking limits. V plus change in V is considered a constant right here because the limit we're taking limit as t is approaching 0. Also, we deduced earlier on that as change in t approaches 0, change in theta also approaches 0. So we're dealing with theta and t right here. So v and change in v is considered a constant, so we brought it outside. Now v plus change in v, it's assumed that the increase is minute, hence negligible, so it's approximately, hence the wobbly equal sign, approximately it's equal to v. Now simplifying the limits, we have v dt, the theta over dt. So let me just take out a little time to show what happened right here. So what happened right here is I took the limit as change in t approaches 0, v plus change in v is out here, so sine, oh my goodness. So our angle, please note, our angle is change in theta, which means all angles are supposed to be represented by change in theta. My sincere apologies. Change in theta. So just take note of that. All angles, all you need to do is just remember to put the change in theta. So back to what I was saying, change in theta divided by change in theta multiplied by change in theta over change in t, delta t. Now what I did was just transform what we have on the left hand side into this. Observe this cancels this, so in the end it's still back same as what we have right there. Now why did I do this? From calculus we know when we take the limit of this, just this right here, sorry, just this right here. Remember, we agreed that as delta t approaches 0, delta theta also approaches 0, which means limit as delta theta approaches 0, sine change in theta divided by change in theta, and from calculus we know this is simply 1, so basically this equals 1, so we're left with limit as change in theta approaches 0 of delta theta divided by delta t. Now again, if you substitute 0 into here, we're going to have an undefined value, rather an undefined answer. So we apply L'Hopital's rule again. We take the derivative of the numerator and derivative of the denominator, and that's what we simplified. Again, don't forget the v in front, which we agreed that is approximately v, so just give an idea of what really went on there. I'm trying to make this as concise as possible. It's expected you should know calculus before this, so this is just a bonus. Now d theta divided by dt is our angular velocity, which is omega. Now also omega is v over r. Playing around with the formulas, we have normal acceleration, is v squared over r, which can also be written as omega square r. Now in this circular motion, that we have our tangential velocity and normal velocity. Tangential velocity acting tangentially to the path, and normal velocity acting towards the center of the curvature. What is the total acceleration? So we represent this again by a vector diagram. So this is tangential velocity, acceleration, normal acceleration, and again angle theta. So the total acceleration of particle is represented from Pythagoras theorem, square root of e t squared plus e n squared, which representing tangential and normal acceleration respectively. Also our angle theta will be equal to tan inverse of our normal acceleration divided by our tangential acceleration. Now a quick summary table of normal versus tangential acceleration. Now tangential acceleration, as said earlier, acts tangential to the path, that is along the velocity direction. Again, we agreed this to be our velocity direction earlier, at point E and at point B to be this. Also, it is responsible for changing speed or magnitude of the velocity. Now note this, responsible for changing speed. So it essentially means it changes how fast, again, just like when you stand up and you're spinning your arm from point E to B, we agreed speed increases. That is why we have V plus delta V. An example of this now, normal acceleration. It acts toward the center of curvature, responsible for changing direction. Now back to the original diagram from point E to B. Now OE is where the normal acceleration will act towards the center. For OB, normal acceleration acts towards the center. Now E normal at OE and E normal at OB, you can see there's a change in the direction. Initially the direction was here, let's say east. Now the direction is moving here, let's say southeast. So just give a picture, an idea of what's going on here. So I simply put changes where you're headed. Now example of normal, a car turning at constant speed. Take note of the underlying constant. Its tone tide and whirl in a circle at constant speed. Another example of normal speed, normal acceleration. Now, as I said earlier, acceleration depends on velocity, not speed. If speed is constant, acceleration is not equal to 0, because acceleration is change in velocity divided by change in time. So if change in velocity is constant, which means v1 and v2 are same, v1 equals v2, v2 minus v1 equal to 0 divided by delta t. Now 0 divided by any number is 0. So acceleration is 0 if the velocity is constant, not the speed. That's essentially the nugget here, the takeaway. Now let's take some cases. Case 1, straight line motion at constant speed. This is our straight path. This is, let's say, our car. Now at constant speed, now take note of the key terms here. It's moving in a straight line. That straight line motion at a constant speed. It's not clearly stated, but what they are saying is the direction is constant here, the speed also is constant. So basically what the statement just said is it has a constant velocity. Now remember, anytime we have a constant velocity, change in v is 0. Now our tangential acceleration is dependent of changing v, sorry, dv divided by dt. Hence, y our tangential acceleration is 0. Now, this is a straight line motion, and we've established earlier our normal acceleration is dependent on radius of curvature. In a straight line, from Euclidean geometry, when a circle has infinite length flattened out, we get a straight line. Simplest example of this is the latitudes of the Earth. Let's just take the equator. As you walk around the equator, you don't really feel like you're in a curve on the Earth. It feels straight, kind of. So just use that picture to visualize what that statement means. So basically, an is given as v square over r. Now our r is infinite, which means infinity. Now anything 1 over infinity is 0. So that is 0. Case 2, straight line motion with changing speed. Now look for the keywords. Straight line motion with changing speed. Direction is given, the speed is changing, which simply means the magnitude of the velocity is changing. Therefore, at will not be equal to 0 because dv will not be 0. However, an will be 0 because it's still a straight line, as explained earlier. And here is a judgeable note of that. Case 3, circular motion at constant speed. Now we know at each point that we take, let's see here, read here, or here, the velocity is going to be tangent to that point. Now speed is again a magnitude of velocity, which means this statement just means our velocity is constant. Now because we have a constant velocity, tangential acceleration will be 0. But because this is a circular motion, a radius of curvature will be there, hence normal acceleration will not be 0. Example, a satellite in circular orbit. Here's a judgeable note again. Case 4, circular motion with changing speed. At will not be 0 because change in velocity is not 0. En will not be 0 because there's radius of curvature. Total acceleration, because we have both a normal acceleration and tangential acceleration, will be given Pythagoras theorem, as we covered earlier, to be this. We've come to the end of this video.